Okay, so let's take a look at this sample problem. So it says the deflecting plates of an inkjet printer with superimposed coordinate axis and ink drop with a mass of 1.3 times 10 to the negative 10 kilogram and negative charge of magnitude capital Q equals 1.5 times 10 to negative 13 coulomb enters the region between the plates. Initially move along the x-axis and with speed Vx equals 18 meters per second. The length of L of each plate is 1.6 centimeter. The plates are charged and thus produce an electric field at all points between them. Assume the field is downward direct, uniform, and has a magnitude of 1.4 times 10 to the 6th power Newton per coulomb. What is the vertical deflection of the drop at the far edge of the plate? The gravitational force of the drop can be neglected. OK， 就是说我们忽略这个重力，我们假设只有这个电磁力或者是这个静电力在作用。Okay, so what we know is that along the x-axis it will be a uniform movement, uniform speed movement. So actually we can simply calculate the time t that the charge will be in the region in the region of this orange box. Okay, so actually t equals so L is 1.6 centimeter here. This is L, and then the Vx is 18 meter per second. So we have 0.016. Okay, actually cm is not a SI unit, so we need to convert it back to meter. Okay, it will be 0.016 meter. Okay, so 0.016 over 18 So that will be 8.89 times 10 to negative 4 second. Okay, so actually we also would like to know the force acting on the ink. Okay, so F equals QE. Okay, and actually we already know this, or maybe I put it as a capital Q because this one is capital Q here, and then we also know the E field. This is the E field. Okay, so we just need to plug in all the number. So Q is 1.5 times 10 to the negative 13 power, and then times E is 1.4 times 10 to the 6th power. So it turns out to be 2.1 times 10 to negative 7 Newton. Okay, so this is the force acting on the ink. Okay, so in mechanics you already know y equals 1/2 at square. This is you should have learned this in high school physics. Okay, so and actually according to the Newton's second law of motion, A equals F over m, so F over 2m times t squared. Okay, and then we already know F is here, T is here, and then M is also here. M is also here, so we just need to plug in all the number. Okay, so this is 2.1 times 10 to negative 7, and then over 2 times 1.3 times 10 to negative 10, and then t is 8.89 times 10 to negative 4 whole square. So we finally find that this is actually 6.4 times 10 to negative 4 meter. Or you can write it as 0.64 millimeter square. Okay, actually, usually we will use the scientific prefix and make this to be between 1 and 1000, but yeah, sometimes 0 point something is still okay. It depends. It depends. So, but here what I want to supplement is that there is something called a scientific prefix. SCIEN, scientific prefix. Scientific prefix. You need to remember. You need to remember. Okay. So starting from 1 is nothing, and then 10 to the third power. 1 is nothing. 1 is nothing. Okay, and then 10 to the third power is kilo. Kilo. Okay, and then 10 to the sixth power is mega. Okay, and then 10 to the ninth power is giga. Is giga. Okay, 10 to the 12 is tera, but yeah, if you are familiar with the hard disk, you know tera will be the next one. Tera. Or for us, I'm working on the AI computing circuit, so tera is a scientific prefix frequently occurred for the performance of the AI hardware. Okay, but I think in physics up to here is already enough. Of course, if you check, you also can see it 10 to the 15 power, 10 to the 18 power, but I seldomly use that, so I don't remember either. But I will say you need to remember. You need to remember up to 10 to the 9th, and also down to 10 to negative 15. Okay, you need to remember in the quiz or exam in this course. Okay, of course in the quiz or exam, if you would like to ask some meaning of a word, I will answer, or TA will answer. But if you ask, what is G, what is M, I will not answer. I will say I have already mentioned it on the class that you need to remember the scientific prefix. Okay, so down there will be, maybe we can also have something like 10 to the negative 2 is C, okay, centimeter, but yeah, that is mainly used for the centimeter, okay, seldom used for others. Okay, if you really need to know 10 to the negative 1 is D, I don't know the full name of it, yeah, but D will be stand for 10 to the negative 1. Okay, sometimes we will call 1dm, which is referring to 0.1 meter. Okay, but yeah, still very is quite rare to use this D. Okay, so maybe you can just ignore these two. Okay, I think you should know centimeter in primary class. Okay, so up there will be 10 to negative third, will be milli. Okay, so frequently you can frequently see this millimeter or milliliter. Okay, and then 10 to the negative 6 will be micro. Micro is a Greek letter. So you need to distinguish milli and micro. 一个是毫，一个是微。And then 10 to the negative 9 is n, so nano. OK， 就是纳米什么，就是那个半导体的话是什么纳米。And then 10 to the negative 12 is pico. OK， 常常听那个什么皮秒镭射啊，皮秒镭射就是这个 pico 啊。And then 10 to the 15 is femto， 就是非啊。Okay, 10 to the negative 18 is ARTO, but seldomly used in the physics class. So I will say you need to remember this three and this 5. Okay, so you need to remember. Yeah, it will occur in some of the question. Okay, just tell you, oh, this is the wavelength will be how many femtometer or something like that, or picometer, something like that. Okay, so this is the scientific prefix. So so you need to remember it. And finally, in this chapter, we will talk about the dipole. Putting a dipole in an electric field, what will happen? Okay, so the quick answer is there will be a torque on the electric dipole of the dipole moment P when placed in an external E field given by a cross product. Okay, so the external E field, we assume the E field is uniform. Okay, uniform in magnitude and also pointing to the same direction. Okay, so inside the whole space, we assume there is a uniform E field, and in this figure it's pointing to the right side, and then we try to put a dipole. Okay, somewhere. Okay, not actually parallel to the E field. Okay, and then there will be a torque. There will be a torque. Okay, so this is tau. Okay, also a Greek letter, which is P. P is the dipole moment. Is the electric dipole moment cross the E field. Okay, so the cross product. Yeah, I suppose you should also have learned that in high school physics for the magnetism. Okay, I don't try to go through it right now because we will also cover the cross product later in this semester. But simply speaking, you will try to use the right-hand rule to determine the direction of the cross product. Okay, so here for this example, we have this dipole. Okay, this is the negative charge, this is the positive charge. So the dipole moment P is pointing to the top right. Okay, and then we also assume that the E field is pointing to the right side. Okay, pointing to the right side. So using the cross product, it's like you use the forefinger pointing the direction along the P. Okay, actually the first vector. Okay, in this case is P because we are considering tau equals P cross E. So P is the first vector, so P is pointing to the top right. Okay, and then you cross to the second vector, which is E, which is pointing to the right side. So the form will be pointing into the page. So in that case, tau is pointing into the page for this. Okay, of course, I should write it on this dipole. Okay, but actually this tau is pointing into the page. Pointing into the page means what? According to the right-hand rule, at this moment the dipole will be rotating like this, like clockwise, but it will swing somewhere to here. Okay, somewhere to here. Okay, the dipole moment will look like this, a negative Q and positive Q, and then up to this point it will swinging back. Yeah, because at this situation, the P is pointing to the lower right, okay, bottom right, okay, and then you use a cross product pointing to bottom right and then cross to the right side, your thumb will be pointing out of the page for this case, okay, so in that case, it will swinging backward, okay, so it's just like at the beginning, it is something like this, and then it swing to here, and then swinging back, and then going back and forth, something like that. Yeah. So there will be a torque acting on this electric field, and then if you need to calculate the magnitude of this cross product, it will be the magnitude of the P times magnitude of E and then times sine of theta. Theta is the angle between these two vectors. Okay, so this is the torque, the magnitude, and the direction. And then we will also have something called the potential for the potential energy U. Potential energy U will be nothing but negative P dot E. So these are the two main operation for the vectors. One is the cross product, and the other one is the inner product or the dot product, depending on how you call it. Okay, so we have a negative P dot E, and actually the value will be P times E, okay, P times E times the cosine of theta. Theta is also the angle between these vectors. Okay, so in such a way, when is this U take the minimum value? When is this U take the minimum value? Is that we have a negative sign here, and then these two are positive. These two are the magnitude of the vectors. So P and E are positive. So which means that when cosine of theta take the maximum value, the whole U take the minimum value. Okay, so when theta equals 0 degree, cosine of theta is maximized, so the U is minimized. Okay, so which means that if originally this dipole and the E field, this dipole moment and the E field points to the same direction, then it remains stationary. 就是它会静止的。如果你一开始的状态是那个 dipole moment， 就是那个电偶距跟这个电场指同一个方向，它也没有旋转的那个角速度的话，它就会静止在那边，因为它是位能最低的状态，它就不会动。它一开始如果有个角度，它就会有位能。有位能的话，它就会转到一个位能最低的位置，然后全部都转成那个角速度或者角动能，然后它就会继续往另外一个方向晃到所有都转回去位能的话，它就换回来，就是那个类似那个简谐运动那样。OK。Okay, so this is pretty much it. We don't try to go too deep. Okay, so here with as additional example. So here it says a clock face has negative point charge negative Q up to negative 12Q. Fixed at the position of the corresponding numerals. The clock hand do not perturb the net field due to the point charges. At what time does the hour hand point in the same direction as the E view vector at the center of the dial? Okay, so actually it just asks you the direction of the E view. So at what time is just easy traced. Okay, so here we have a clock. Okay. 不行。Should be something like this. Well. Okay, so here we have a circle, and then okay, just like the clock like that, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, something like this, and then it just tells you that for the numeral number, it has a negative q all the way up to negative 12q, which means it has let's say here we have here we have negative q, negative 2q, and then all the way up to here negative 12q here. Okay, so we have many point charge at different numeral positions. Okay, and so in that case we can, so it actually asks you what is the E field at the center, what is the direction of the E field at the center, and then the hint is to use the symmetry. So clearly we can see that for the symmetry to the center point, okay, 1 o'clock should be 7 o'clock, negative 7q. Okay, so in such a way, so here we first consider this negative 7q and negative q and negative 7q. And then as much as this is a negative charge, so it generates E field pointing E1 like that, and then E7 like that. And as much as they are pointing to the opposite direction, and then this is negative 7q, this is negative q, so it will be something like okay, so you can consider it is something like, or at the 7 it only have a negative 6q. Okay, so if you only consider negative q, negative 7q here, and then if you consider negative 6q here, okay, so it will generate the same thing. And similarly, if you consider negative 2q and negative 8q, okay, they will partly cancel either. Okay, so it turns out to be here at 8 we have a negative 6q. Okay, similar to that. Okay, so this negative 2 can partly cancel with this negative 8 down to a negative 6q. So on and so forth. So at 9 we also have this negative 6q, and then at 10 we also have this negative 6q, and then at 11 we also have this negative 6q, and then at negative 12 at 12 we also have this negative 6q. Okay, so we only have this all the way negative 6q at 7, 8, 9, 10, 11, and 12. Okay, so when we consider at the center point, okay, so all of these vector points to the have the same magnitude, although pointing to the different direction. But you can simply consider that for, let's say, for 7 and 12, okay, so they will actually point to the direction right in the middle between 9 o'clock and 10 o'clock, which is actually 9:30. Okay, so for the 7 and 12, and then for the 8 and 11 also they will point to this direction, and then for 9 and 10, okay, it will also pointing to the direction at 9:30. Okay, so the answer will be 9:30. Yeah, because if I need to draw it all the way, so it will be, there will be quite a lot of E field pointing to 7 o'clock, 8 o'clock, up all the way up to 12 o'clock with the same magnitude. Okay, so you can easily check that. the overall E field will have the direction pointing to 930. Okay, so we have another one. So here it says, suppose you design an apparatus 就是一个装置 in which a uniformly charged disk of radius r to produce an electric field. The field magnitude is most important along the central perpendicular axis of the disk at point P at distance 2r from the disk. Cause analysis suggests that you switch to a ring of the same outer radius r but with the inner radius of r over 2. Okay, so it means that here we have a disk. Originally we have a disk with a uniform charge density, and then here it asks due to some reason we need to reduce the cost. Okay, because for the material itself, for the conductor, it costs you money. Okay, so it asks, it just said that we would like to remove the inner half of the part of the inner, we would like to remove the inner part of the circle. Okay, inner part of the circle up to the r over 2. So here is that assume that the ring will have the same surface charge density as the original disk. So 所以他就说就是他会拿走这个部分，那部分的电荷也一起拿走，所以的话就是密度是保持不变的。Okay, if you switch to the ring, by what percentage will you decrease the electric field magnitude at P? Okay, 就是问你那个电场变弱了多少。Okay, so let's call this EA. Let's call it the part A. So for EA, we will recall the formula. E equals sigma over 2 epsilon naught 1 minus z, and then over square root of c squared plus capital R squared. Okay, so this is what we derive today, previously. Okay, so we would like to make use of these results. Okay, so in that case we have a finite R, so that we don't have the R much larger than z, or R tends to infinity assumption, so we still keep this expression. Okay, so in this way we need to adopt to this case. Here we have the radius to be capital R, and then here the distance P to the disk will be 2R. Okay, so which means z equals 2R. So in this way we have a sigma over 2 epsilon naught, and then 1 minus, okay, z to be 2R, and then over square root of 2R squared plus R squared, like this. Okay, and then we can do some cancellation. It turns out to be sigma over 2 epsilon naught, and then 1 minus 2 over square root of 5. Okay, and then for question, and then here we try to calculate the E field generated by the hollow part. Okay, for the hollow part. Okay, if we can calculate the hollow part, and then we can subtract EA by the hollow part, and then we will know the E field generated by this blue disk. Okay, so for the hollow part, we can still adopt the similar, actually this expression, but with little bit change. Okay, so the only difference is that we still have a sigma over 2 epsilon naught, because the surface charge density doesn't change at all. And then we have 1 minus, the distance is still z equals to 2r. So we still have 2r here, and then square root of 2r squared. But here, for the hollow part, the radius is reduced to half of r. So here we have a half of r squared. So in such a way, this is actually sigma over 2 epsilon naught and then 1 minus 4 over square root of 7. Okay, so actually it just asks you how many percentage you decrease the electric field magnitude at point P. Okay, so which means that this percentage of reduction is actually E whole over EA. Okay, so it will be sigma over 2 epsilon naught and then times 1 minus 7 over square root of 2 over sigma over 2 epsilon naught and then 1 minus 2 over root 5. Okay, so okay, most of this can be cancelled and then the remaining the root expression. So and then actually you can also multiply it by 100%. Okay, it asks you the percentage. So finally, pressing the calculator, you can get this is 28.3%. 28.3%. Yeah. Yeah. So this is not that difficult. We can actually make use of the expression derived previously. So actually, for the quiz or exam or even the selected problem, for some of the case you still can make use of the formula that was derived during the class. And then actually during the quiz and exam, I will give you a page of formulas so that you don't need to remember those formulas. If you need to remember some other formula, you can remember by yourself. But yeah, actually you can just skip those parts. You only need to know how to use them. Will be sufficient. Okay, so actually